Hi folks, we're taking a look here at number 15 from page 99. So they give us this function P, which represents the population of fish in a lake over a period of 12 years. Okay, and at year 6, catastrophe occurs, there's a chemical spill, and that changes the model for the fish population in the lake. Okay, and it looks like they want us to investigate what's going on around that time that the spill occurred. Okay, so the first thing they asked us to do is to sketch the graph of the function, but I'm actually going to see that I don't really need the sketch. I'll show you afterwards on Desmos, but we don't really need the sketch to solve this problem. So let's go ahead and think about how we would find these limits. So here we're looking for the limit of the population as t approaches 6 years from the left. Okay, so that means we're only interested in t values that are less than 6 for this limit. We actually don't care what happens at 6. And we notice that this is going to be the equation that we're going to work with, because this equation is valid for all the t values less than 6. Okay, now the other thing to notice here is that this is a quadratic function. Quadratic function is a nice function whose limit is always equal to the function value. Okay, so normally we can't make that assumption, but knowing that this is quadratic, it's going to have that property. So in order to find what the function values approach as t approaches 6, I just have to find the function value at 6 for the ones that include all the t values I'm interested in, which are only those that are less than 6, because I'm approaching from the left. So let's calculate this. 3 plus 1 over 12 times 6 squared. So 36 divided by 12 is 3, plus 3 is 6. And I believe it's in thousands. So this represents 6,000 fish at this point here. Now, when we want to determine the limit as t approaches 6 from the right, well, now we're only interested in t values that are larger than 6. And this is going to be the equation that gives us the function values when t is larger than 6. So again, the only thing we care about is what's happening as t approaches 6 from the right. So the fact that this is not defined when t is equal to 6 is of no concern. However, what this function will approach as t approaches 6 from the right will just be the function value from this equation. Okay, so in order to determine this limit, we just have to calculate 2 plus 1 over 18 times 6 squared. So 36 divided by 18 is 2, plus 2 equals 4. So 4,000 fish. So again, because they're both quadratics, you know, the limit will just approach the function value, but because we're approaching from the left, we use the equation that describes the values when t is less than 6, and when we're approaching from the right, we use the equation that describes the t values when they are greater than 6. Okay, so now from here, we can just answer question C very easily. It's just 6,000 minus 4,000, so it looks like 2,000 fish were lost in this catastrophe. Okay, now let's just take a quick look at the graph, okay, to see that everything fits. So here, as we expected, we have a quadratic to the left of 6, another quadratic to the right of 6. However, the limit does not exist at 6. Okay, so from the left, as we approach 6 from the left, we see that we use the left-handed function to determine the limit, but when we're determining the right-handed limit, we use the right-handed function to determine the limit. And not surprisingly, they're not the same. So here from 6,000 to 4,000, 2,000 fish were lost. Okay, now what we want to know in the next part is when will the population recover? Okay, so since we're talking about after the catastrophe, we need to work with the right-handed function. So even looking at our graph, it looks as though it might be maybe around 8.5 years. Okay, or at that point, so it'll take about 2.5 years for them to recover, but we're going to do this analytically. But what's important here is because we're interested in the times after the chemical spill, we're going to be working with the second function. So what we want to know is when will this second function again be equal to 6? In other words, the population right at the point of the oil spill. So here we've got 2 plus 1 over 18 times t squared, and we need to know when that is going to be equal to 6, okay, which represents 6,000. So now this is pretty easy to solve. 1 over 18 t squared equals 6 minus 2 is 4, so t squared is equal to 4 times 18, so that's 4 times 10 is 40, 4 times 8 is 32, so 72. Okay, and so t squared is equal to the square root of 72. Okay, so again, looks like it's not going to be exactly 8.5. Let's calculate what that is. So square root of 72 is equal to 8.49, so about as close to 8.5 as we can get. So t is approximately equal to 8.49 years. Okay, so if they want to know how long, and I'll just take a look at exactly, it says at what time did the population recover, so I guess we can say 8.49 years from the start, or you can also say relative to the spill itself, 2.49 years from the spill. Okay, since they didn't really specify, either one of these would be valid. Okay, another thing here, remember we did take a square root, but of course we only considered the positive square root because we were interested in time. We weren't interested in any negative values here. Okay, so that's it. But again, I want you to keep in mind how we were able to solve this problem without actually sketching the graph. The graph's a nice visual, but in the end, if you understand how these limits work, there's no need to actually sketch the graph. Okay, that's it.